Okay, then hello everyone. It's my great pleasure to welcome you today to our international online seminar on interval methods and control engineering. And it's my great pleasure today to have Thomas Liu here, who is the very first speaker in 2024 in the series of our seminars. And to introduce Thomas, he's currently working as a researcher at Toyota Research Institute. Before that, he completed his Bachelor of Science degree at the École Polytechnique, École Polytechnique de Lausanne?
Yeah.
Afterwards, he did his Master of Science at the ETH Zurich. And yes, this was in 2019. And he obtained his PhD degree in aeronautics and astronautics from Stanford University in 2023. And today he'll talk about the exact characterization of the convex hulls of reachable sets. And Thomas, we're looking forward to your talk.
So thank you for the introduction. Thank you for the invitation to give this talk, and thank you for coming to this presentation. So I'm excited to present our recent results with Professors Riccardo Bonelli and Marco Pavone. And in short, we derived an equation that we believe simplifies the computation of efficient approximations of reachable sets of a class of nonlinear systems. So this should be of interest to people in this seminar who are working on verification, safety critical control, and interval methods. But first, let me motivate this work. So we're designing control systems that are becoming increasingly complex. And this is because we need them to perform increasingly complicated tasks in high uncertainty environments. So for example, we're designing control systems for power grids that can handle uncertain production and demand. We seek Mars rovers that can navigate on other planets and handle uncertain wheel-soul interactions, and are designing autonomous cars that drive in uncertain road conditions and interact with other agents. So I'll argue that by explicitly accounting for uncertainty, we can design control algorithms that are robust. So for example, consider a spacecraft that grasps the payload and has uncertain dynamics and seeks to bring this payload to the space station. To explicitly reason about uncertainty, this system should be able to understand how uncertainty propagates forward under the action of a sequence of control inputs. Then with these uncertainty envelopes, it should be able to compute trajectories that avoid obstacles in the presence of uncertainty. Now, the tighter these uncertainty envelopes are, the better. That is, if these reachable set estimates are too conservative, the robot will need to take a detour and use extra fuel to accomplish its task. So this talk is about reachability analysis, that is about the structure of these reachable sets, how to compute them as efficiently as possible. Specifically, we derive an equation that gives information about the structure of the convex hulls of these reachable sets. So our work is motivated by applications. For example, in robust model predictive control, one builds uncertainty tubes and use them to robustify constraints around the nominal trajectory and make sure that constraints are robustly satisfied and that the system is stabilized under uncertainty. Now, what you'll find is that for computational reasons, many algorithms return convex over-approximations of the reachable sets. For example, parameterized as ellipsoids or as rectangles. And there is a wide range of tools to compute these convex over-approximations. One big category of these algorithms are what I call single-step propagation methods. So what they do is that at every time step, they build an approximation of the reachable set of the system. And so at every time step, the previous estimate is propagated forward to build an estimate of the reachable set at the next time step. And so these methods proceed one step at a time, propagating these estimates forward. And what we observe is that these methods tend to be quite conservative. They're fast oftentimes, but they tend to be conservative because they don't fully exploit the structure of the problem. So I'll argue that today, for many problems of interest, existing methods remain either too slow, that is, they don't run in milliseconds on computationally limited hardware, or they remain too conservative to be used for closed-loop control. So in this work, we were wondering, is there additional structure that we can use to design more efficient algorithms? So we studied the following class of nonlinear systems. So we study systems parameterized by an ordinary differential equation, an ODE, where X denotes the state of the system, F the nonlinear dynamics, and W disturbances that are always in a set of disturbances that is bounded. And we study the reachable sets of the system, that is all possible states where the system could be at time t for any possible disturbance signal W. More precisely, we study the convex holes of these reachable sets. That is the tightest possible convex over-approximation of the reachable sets. Now, this problem is challenging because the reachable sets a priori are the image of an infinite dimensional set of disturbances. That is, disturbances are in an infinite dimensional space of functions. They're functions that are signals over time. So a priori, we may need to look at very complicated disturbance signals that could oscillate over time and even be discontinuous. They could have jumps. And so computing the reachable sets a priori amounts to studying all possible trajectories for all these disturbance signals, which is intractable. So many methods to circumvent this problem study a discrete time formulation instead. So because if one considers discrete time formulation, these oscillatory phenomena disappear because there can be only finitely many switches. So when you consider a discrete time formulation, you end up with a finite dimensional problem that is generally easier to study. Now, I'll argue that oftentimes these type of algorithms tend to be sensitive to the choice of discretization. So what happens is that if you double the number of discretization steps, the conservatism may increase with these methods. In contrast, by directly studying the continuous time formulation, we hope to design algorithms that are more robust to the discretization, specifically algorithms that, as the discretization of the problem is refined, return more accurate approximations. And importantly, what I'll show today is that studying the continuous time formulation gives additional structure that we can use to design more efficient algorithms. Specifically, what we proved in this work is that under two assumptions that are introduced in a little bit, the convex holes of the reachable sets are exactly the convex holes of the image of a function f for all possible disturbance values at time 0 on the boundary of the set of disturbances. So here f, the map f, gives the solution of an ODE. And what this result states is that the true convex holes are actually the convex holes of solutions of an ODE for different initial conditions on the boundary of the set of disturbances. So this is great because starting from a problem that was infinite dimensional, we end up with an equivalent problem that is finite dimensional, that amounts to studying solutions to an ODE. So we can design an algorithm where we sample different initial values of the disturbances. We integrate this ODE, which will give us trajectories of the disturbances and trajectories of the states. And if we take the convex hole of these state trajectories, we then will end up with good approximations of the convex holes of the true reachable sets. So now what I'll do is dive a little bit deeper into the assumptions and the details of this result. So our work relies on two assumptions. First, the dynamics should be smooth enough. That is, they should be Lipschitz, the gradient should be Lipschitz, and f should be continuously differentiable. And two, the set of disturbances should be compact. So it should be bounded and closed, and its boundary should be an ovaloid. That is, the set of disturbances should be strictly convex and have a smooth boundary. Now, under this second assumption, the Gauss map of the boundary of the set of disturbances is a diffeomorphism. And so the Gauss map returns for any point on the boundary of the set of disturbances the normal vector at this point. So it gives us the perpendicular direction to the surface of the set of disturbances. And so for many for many sets of interest, like ellipsoidal sets or ball sets, the Gauss map and its inverse have nice closed form expressions. So our main result is as follows. Let's define this augmented ODE, where the state follows this equation here as a function of the Gauss map and a curve Q. And the curve Q follows this equation where we have a projection operator onto the tangent space of the sphere, the gradient of F and Q. And this augmented ODE is parameterized by the initial value of the disturbance that through the Gauss map gives us the initial value of this curve Q. Then if we define this solution map of this ODE, which gives us the state at time t starting from this initial disturbance value and solving this augmented ODE, we have a theorem that says that under these two assumptions I presented before, the convex holes of the true reachable sets are exactly the convex holes of solutions of this augmented ODE for all possible initial values of the disturbances at time 0 on the boundary of the set of disturbances. So again, this result is a finite-dimensional equivalent description of the convex holes of the reachable sets. So what I would like to do next is to dive into the proof of this result so you know how it's derived and so you get more insight into the geometry of the problem. So the first idea we had was that if we want to know the convex holes of the reachable sets, then we only care about boundary states. So we only care about states that are on the boundary of the reachable sets. So let's define such direction D, and let's look for the reachable state that is the furthest in the direction D. So this gives us an optimal control problem where we maximize the direction, we try to push the reachable states in the direction D, subject to the dynamics, over all possible disturbance signals. And the goal is to get this boundary state. So we could solve this via nonlinear optimization, but this could be computationally expensive, or this could be stuck in local minima. So we were wondering if there is more structure about the problem that we can use. So specifically using calculus of variations or the Pontryagin maximum principle, so the PMP, allows us to reformulate the previous problem as a boundary value problem. That is, for any locally optimal solution of the optimal control problem I showed before, there exists an adjoint vector Q, so a trajectory, that solves this boundary value problem, where Q dot follows this equation as a function of the Gauss map and the adjoint vector trajectory, and Q dot follows this equation here that I introduced before. What's interesting to note here is that the final value of Q is exactly the such direction D. And in fact, you can show that Q always points in the normal direction of the reachable set boundary. So what you see here is the value of the disturbance. So because we made this assumption about the set of disturbances, if we know the value of Q, we know the value of the disturbance through the Gauss map. So the value of Q is always perpendicular to the boundary of the set of disturbances. And so if we know the value of Q through the inverse Gauss map, we know the disturbance value as well. So this is good because starting from a problem where we optimize over all disturbance signals, we end up with a problem that amounts to looking for a variable that's in a finite dimensional space, so on the sphere in n dimensions. So now, again, we could solve this boundary value problem, and there are good methods for doing so, specialized to different systems. However, we could still have this problem of being stuck in local minima, or this could be computationally expensive. So we were wondering, is there a way so that we can design an algorithm that doesn't require solving these boundary value problems? So the next idea we had was, what if we knew the initial value of the disturbance? So because there is a one-to-one mapping between adjoint vectors and disturbance signals through the Gauss map. If we know the initial value of the disturbance, then we will also know the initial value of the adjoint vector. And so if we know the initial value of the disturbance, we end up with an ODE that is parameterized by this value that we can integrate to get the solution to the boundary value problem. So if we knew the initial value of the disturbance, we would end up with an ODE that we can integrate and gives us the full trajectory for Q and X. Now the problem is, again, we don't know what this initial value of the disturbance is. So our final idea was to say, okay, let's try all of them. Let's try all possible initial values of the disturbances on the boundary of the disturbance set. And so basically the end of this result just says that by trying all possible initial values of the disturbance and integrating this ODE, we will end up with all possible trajectories of the states that are always on the boundary of the convex holes of the reachable sets. To be more precise, if we try to integrate this ODE for all possible initial values of the disturbances, we will not miss any boundary states. And so if we take the convex hole of all of these states that solve this augmented ODE, we will exactly get the true convex holes. And so this is exactly what this result says, that the true convex holes of the reachable sets are exactly the convex holes of all possible solutions of this augmented ODE for all possible initial values of the disturbances. And so, as you could see, this result came from this nice connection between geometry, optimal control, and reachability analysis. And so this beautiful connection is well known in the literature and has been studied for decades. Now, the most relevant work in this area is a beautiful paper by Krenner and Schäppler in '98 that explicitly characterizes the reachable sets of systems with nonlinear systems with a small number of inputs. So this paper is great because it exactly characterizes the true non-convex reachable sets of a certain class of nonlinear systems. Now, if you read the paper, you'll see that it relies on a small time assumption. That is, they assume that the horizon is small enough. And so they cannot handle arbitrarily large prediction horizons. And the reason for this is that even if we have a smooth nonlinear system, initially its reachable sets will grow, and it's potentially, it's a possibility that they will end up curving over themselves and self-intersecting. And these self-intersections break the smooth submanifold structure of the boundary of the reachable sets. And so this makes the mathematics more complicated, and to prevent these kind of self-intersections, you need small time assumptions. What's beautiful here is that when we take the convex holes of these reachable sets, we convexify the reachable sets, and all these self-intersections disappear because we fill space. So you can show that actually the boundary of these convex holes is always smooth under the assumptions I presented. From a practical standpoint, this means we don't need these small time assumptions like in previous work, and so this gives us a result that's easier to use for algorithm design. So we can show that if we design a sampling-based algorithm that consists of sampling initial values of the disturbances and returning the convex holes of the state trajectories, solving this ODE, then if we take a sample of these initial conditions that is dense enough, and if the dynamics are smooth enough, then we'll get good approximations of the true convex holes of the true reachable sets. So we tested this result on this algorithm on different systems. So here in a 2D system with linear dynamics and a neural network controller, we studied what the reachable sets, what the convex holes of the reachable sets of the system look like. And so we compared with a formal method tailored for these systems. and with a naive Monte Carlo-based method that consists of returning the convex holes of sampled trajectories where we sample the values of the disturbances at each time step. And so what you can see is that our algorithm outperforms both methods in terms of estimation error and in terms of computation time. And so the reason is that the formal method, while it is guaranteed to return over-approximations because it really uses the structure of the dynamics and its properties, it is also more conservative because it propagates uncertainty one step at a time. The Monte Carlo-based method returns under-approximations of the true reachable sets. Now, both of these baselines are quite sensitive to the choice of discretization. So if we double the number of discretization time steps, we'll get worse performance with both of these methods. In contrast, our method, because it only requires sampling initial values of the disturbances, it's agnostic to the choice of discretization. So its sample complexity does not depend on the choice of on the number of discretization time steps. So it will only get more precise as we increase the resolution of the discretization. And so by using the structure of the convex holes, we get an algorithm that's more efficient. We also tested it on a system with spacecraft dynamics, where we try to compute the reachable sets of angular velocities under the action of disturbances. And we compared with, again, a Monte Carlo-based method that returns under approximations, and a Lipschitz-based method that overly estimates the reachable sets. We were able also to use these reachable set estimates from our algorithm to design a robust model predictive control algorithm that stabilizes a system while robustly satisfying constraints under the action of disturbances. And so what you see here is our rollouts of the controllers, so closed loop simulations for different initial conditions and random disturbance perturbations. And for all cases, the controller stabilizes the system and satisfies all constraints. And so on with a Python implementation, 100 samples running on this laptop, we're able to replan at 10 Hertz. And so since it's a sampling-based method, we believe we can parallelize the implementation and get good empirical performance in the future as well. So with this, I presented structural results about the convex holes of reachable sets that informs the design of efficient estimation algorithms. And we're currently extending these results to also consider uncertain initial conditions, more general disturbance-affine dynamics, and uncertainty sets whose boundaries are not necessarily ovaloids. So for example, rectangular sets of disturbances. Another interesting result is that we don't use here is that the boundary of the convex holes of reachable sets is always smooth, so has a nice submanifold structure. So you can use this to derive better error bounds that are quadratic in the resolution of the sampling scheme for our sampling-based algorithm. And so these error bounds are tighter and better explain the good empirical performance of the algorithm that we presented. And so now I think there are lots of opportunities for designing algorithms that outperform the sampling-based method for reachability analysis. That is, we have people who are experts in polynomial systems, in systems that satisfy mixed monotonicity conditions, and so on. And all these properties we did not use in the design of our algorithm. So I believe there is potential for future work that combines our geometric results from optimal control with additional properties of the dynamics to design better algorithms for reachability analysis by studying solutions of this ODE. And this should have nice applications for the design of efficient, robust controllers. I would like to thank our funding sources, so that is NASA and the Toyota Research Institute, and say that all our code is in Python and is available on GitHub. And with this, thank you very much for your attention, and I'm happy to take any questions.
Okay, many thanks, Thomas, for a very interesting presentation. And yes, I'll just take up your question that you asked at the end. Is there someone who wants to know anything additionally? Okay, at the moment, I do not see any raised hand, but I have taken some notes in between. And yes, you have almost stolen one question of mine at the end in your Outlook slides, taking into account some specific structure. And I think it's not only the mixed monotonicity approach that you mentioned that we also had a few weeks or months ago here in the frame of the seminar, in fact, in 2 presentations. One other thing is maybe also directly related to modeling. Maybe that people who are deriving the state equations directly by taking into account first principle approaches, that they keep in mind that they have those specific monotonicity properties already reflected in the state equations, and that they formulate the system models in such a way that everything that obeys those cooperativity properties, the monotonicity properties in your function, this was the small f, and everything that doesn't satisfy those monotonicity properties would then be shifted into the disturbance into the W. And I think this would also be a nice trade-off for people who have in mind how to model a system which that they want to use afterwards for reachability analysis. From my point of view, this would also be a very nice extension.
Yeah, that's an exciting idea. I didn't think about it. For sure, I think there is potential there as well. So to use these system properties to design these sets for disturbances, for sure, yeah. Yeah, that's interesting.
Yes, and the other thing is this problem that you have shown those self-intersections, especially for discrete time system models. I think they can easily be detected. In a discrete time setting, you would have, I think, a Jacobian from one time step to the next, in which the Jacobian matrix is not regular. And in such cases, you would get something like a set is being somehow, or more or less, you have a convex set, and this is being mapped to something that is self-intersecting at the end. And I think this could also be included here as one of the examples how to detect whether or not such ugly phenomena occur.
That's interesting. I didn't think about it. So I guess this would be about using these results, which I haven't seen applications in estimation of reachability analysis, and trying to remove these small time assumptions by detecting if these self-intersections occur. Yeah, that's interesting because it could give us better algorithms for estimation of non-convex reachable sets. Yeah, I didn't think about it. That's interesting. Okay. Now, if you care about convex holes, maybe you don't really care about this convex, about these self-intersections. So, yep. Yeah, TBD.
Yes, that's true. Now I see a question in the chat. Eduardo, do you want to ask it yourself? Just unmute yourself and go ahead.
Yes, sir. Good morning, sir. Because my main question is, what is the difference? Yes, about this method, about the method exposed by Bell matrices, sorry, or Tagachi-Sugeno method. There are difference, or is the same method? Because the meaning, for example, the vector matrix, we can calculate the sets vertex that are not intersection inside there, and Tagachi-Sugeno also calculate the sets, the convex sets that are not intersection. Did you understand my question?
So to be completely honest, I don't know this Tagachi-Sugeno method, so I can't comment on this. I do know that there are results that ensure that the reachable sets are always convex, so this makes sure that you don't have these self-intersections. But I don't really know how to answer your question. Maybe in case it's clear, these self-intersections are only a problem for the derivation of these results using optimal control. So like in the end, our result doesn't care about self-intersections. As long as we want convex over approximations, we don't really care about the self-intersections. But I think I'm missing something about your question.
Yes, I think this question is directed a little bit in a different direction. I think, Eduardo, but maybe you, please correct me if I'm wrong. I think you're talking more or less about models that are structurally linear, but where your system or the dynamics matrix is uncertain. And then you would cast this kind of system model into a polytopic uncertainty representation. And then you could try to trace some extremal system realizations and form a convex hull.
Okay.
Yes, and this is, I think, yes, maybe a specific case of the thing that Thomas treated during his work, because he allows also for nonlinear dynamics. His right-hand side of the state equations was something an x dot equals some nonlinear function f plus disturbances. And yes, your Tagaki-Sugeno approach would then be approximating with piecewise linear membership functions that are nonlinear dynamics in a more conservative, in a more conservative linear, or in this case, a fine or polytopic representation. And I think, yeah, that's at the end a trade-off, whether over-approximating directly the nonlinear system model by a polytopic linear representation is more efficient from the point of view of computing time. The price you have to pay definitely is the conservativeness of the enclosures. Or if you try to get tighter enclosures and maybe have to pay the price that this sampling scheme that Thomas presented, for example, today, will be computationally more demanding and cost more computing time.
Okay. Okay. Yes, because my question is about you have a differential equation, and the order is more accessible, and with that method is possible to simplify the calculus. But okay, I understand your answer. Thank you.
Nice. Yeah, perhaps the main takeaway is that the augmented ODE that we derived doesn't have disturbances. So it's not a set-valued ODE. So it's equivalent to a problem with uncertain initial conditions, if that makes sense.
Okay, let's see. At the moment, I do not see any raised hand, but I have a question concerning the outlook. At the moment, you're assuming that your system model already includes some kind of controller, or that you're using the corresponding calculated sets, your reachable sets in the future, maybe for replanning trajectories in order to avoid obstacles or whatever.
Sorry.
Do you already think about, or did you already think about, since you mentioned the maximum principle of Patriarchy, to formulate a twofold optimization? One is, for example, like you did at the moment, finding optimal enclosures of the reachable set. And on the other hand, also optimize some performance criterion in order to perform a structural optimization, let's say a minimum fuel problem to go from A to B, time minimal optimal control problem under uncertainty.
Yeah, great question. So that's what we're doing here in the MPC problem. So what we do is that for any control trajectory, our result gives us the reachable sets. Our dynamics are then time varying as a function of the control inputs. So then these reachable sets are a function of the control inputs. So then we can optimize over the control inputs to solve a robust optimal control problem. And so that's how we do this MPC, robust MPC controller, where we embed the reachable set estimates in an optimization loop to do robust optimal control. And this is covered in the in our formulation.
Okay, your control sequences then, are they fully free? Can they vary arbitrarily within this bounded range that you have specified there? Or did you make some structural assumptions, for example, that you restrict yourself to piecewise constant inputs or to inputs that are, let's say, polynomials in time or whatever?
So for the math, as long as the control is integrable and we can, I mean, as long as the optimal controls problem is well formulated, we can handle continuous time control signals. Now, for the practical applications, we discretize over time, assume that the control input is piecewise constant, and then we get a nonlinear optimal control problem that is parameterized by the control values at every time step. And then we optimize over the control signal to get these trajectories that solve the robust optimal control problem. Does this make sense?
Yeah, yes, that obviously makes sense. No, because you have different options how to parameterize your control. You could assume it's really continuous time. You could assume it's piecewise constant, or you could also say that's, for example, something like some unknown coefficients that you're optimizing over, and the function is depending on monomials and time, some a0 plus a1 times t plus a2t squared, and then you would solve a parameter optimization problem. Yes, exactly. And especially the latter option, maybe using some different basis functions, Bernstein polynomials, for example, would allow you to handle also larger time horizons for the optimization with very, very small memory requirement to parameterize the corresponding inputs.
For sure.
This would also be of interest if you have optimal control problems that you want to solve in real time or close to real time over long time horizons where you have significant memory restrictions.
For sure. For sure, yeah. I think now I'd say the biggest limitation of this formulation is the parameterization of these reachable sets. So because we use the sampling-based method, it can still be compute expensive on limited hardware if we have a lot of samples. So for nonlinear optimal control, this can still give problems that are expensive to solve online. So that's why I wonder if there are better methods for reachability analysis that could use our convex Hall characterization and could be easier to then embed in robust optimization problems. In this work, we studied sampling-based reformulation that's still fast enough, because on a computer, it's with 100 samples, it's still doable. But I think there is room for future work in this direction, for sure. Yeah, great point. Thanks for the question.
Maybe a follow-up. Did you do some work where you already implemented this type of controller then on some real hardware instead of pure simulations? So
this algorithm here, not really, but I implemented similar algorithms. So like sampling-based reachability analysis algorithms for robust MPC that I deployed on hardware. Actually, we have in the lab a simulator, so a hardware platform simulating spacecraft dynamics on the plane. And I did embed these sampling-based reachability analysis algorithms to design MPC algorithms. Now, not using this kind of exact characterization, the previous work I did used naive Monte Carlo sampling to compute estimates of the reachable sets. So you end up with an algorithm that's pretty much the same as here, but doesn't integrate this augmented OD and instead just integrates the dynamics. So like we did this, but not using this additional structure. So
yes, that's always from a practitioner's point of view, extremely convincing that you see, okay, there's some real hardware or some hardware in the loop simulation on which this is actually running.
Nice, yeah. I mean, this is what motivated this line of work around sampling-based reachability, that we didn't have when I started my PhD, there were no algorithms that could handle complicated dynamics like neural networks with weights of the neural networks that are uncertain and can be fast enough and not too conservative to be run in an optimization loop. So this led me at some point to study sampling-based algorithms. And I think what's nice is that when you study the properties of these sampling-based algorithms, you have to study the true structure of the reachable sets to derive error bounds. And that's how it led me to study this formulation here with continuous time signals of disturbances for which naive Monte Carlo methods do not work, because if you increase the number of discretization time step, the sample complexity of naive Monte Carlo will get worse. So, and in the end, you don't need to sample at every time step independently. You just need to sample at the initial time if you have certain properties. Yeah.
That's in fact something that is very convincing. Okay, now let me ask the audience again. Is there anyone who wants to ask a question? If this isn't the case, then again, many thanks, Thomas, for your presentation, also for giving this further insight during our question and answer session at the end. And to all of you, have a nice Friday afternoon, have a nice weekend, and we'll meet each other here again in the seminar series on Friday in 2 weeks. Bye.
Bye, thank you.